Welcome to the channel, Tech Enthusiasts. Today, we're diving into a topic that's rapidly transforming the world of software deployment, accelerating Java microservice deployment with AI-driven Dockerization. In the fast-paced landscape of cloud-native applications, Java microservices are everywhere, and Docker has become the de facto standard for packaging them. But how often do we truly optimize our Docker files? Often, this crucial step is manual, prone to errors, and rarely achieves peak efficiency. Imagine a world where your Docker files aren't just good enough, but perfectly optimized, automatically. That's the promise of AI-driven Dockerization, and we're going to show you how generative AI tools can recommend and generate ideal Docker files, complete with sample concepts and pipeline integration. Historically, creating Docker files for Java applications has been a bit of an art form. Developers painstakingly craft each instruction, striving for a balance between image size, build speed, and runtime performance. However, this manual process frequently leads to suboptimal results. We end up with bloated images containing unnecessary build tools, security vulnerabilities from running as root, and slow, inefficient builds due to poor layer caching strategies. These seemingly minor inefficiencies compound over time, slowing down deployment pipelines, increasing storage costs, and even posing security risks. Think of it like assembling a complex puzzle without the picture on the box. You might get it done, but it won't be as efficient or elegant as it could be. This is where AI steps in. Imagine a smart assistant that understands your Java project's dependencies, its framework, and common deployment patterns. This assistant, powered by generative AI, can analyze your source code and, instead of you guessing, recommend, or even directly generate a Docker file that is custom-tailored for maximum efficiency. This isn't just about saving time, it's about achieving levels of optimization that are difficult, if not impossible, to reach manually. We're talking about significantly smaller image sizes, faster build times, enhanced security, and consistent application of best practices across your entire microservice ecosystem. This is a game changer for DevOps teams and developers alike, moving from reactive problem solving to proactive optimization. To illustrate this powerful concept, we've put together a demonstration project called AI OptiDoc Java. This project isn't just theoretical, it showcases a practical approach. At its core, we have a simple Java Spring Boot microservice, a typical Hello World REST API. The magic happens with our simulated AI recommendation script, a Python program that emulates a generative AI tool. While it doesn't call a real large language model in this demo, it embodies the logic a real AI would use to infer and generate an optimized Docker file. We also include a pre-generated Docker file .recommended to show the output, a local build.sh script for hands-on experience, and a GitLab CI/CD configuration to demonstrate seamless integration into an automated pipeline. This setup allows us to explore the entire conceptual flow. Let's start with the application itself. Our example is a very basic Java Spring Boot application. It's a standard Maven project, configured with pom.xml to include Spring Boot Web Starter for building RESTful APIs. The main application class, AI OptiDoc Java application.java, simply exposes a /API/hello endpoint that returns a greeting message. It's designed to be lightweight and representative of any typical Java microservice you might be developing. The simplicity of this application allows us to focus entirely on the Dockerization and optimization process, rather than getting bogged down in complex business logic. This serves as the perfect canvas to demonstrate how AI can take a raw Java artifact and transform it into a highly optimized container image. The real intelligence of our demonstration lies in the recommend_dockerfile.py script. This Python script simulates the brain of our AI-driven system. In a real-world scenario, this script would interact with an actual generative AI service, feeding it project metadata like Java version, framework, Spring Boot, dependencies, and even security requirements. The AI would then process this information, leveraging its vast knowledge base of Docker best practices, security guidelines, and build optimization techniques. For our demo, the script contains predefined logic to generate a highly optimized Docker file, but it prints out the rationale behind those recommendations, making the AI's thought process transparent. This is where the AI identifies opportunities for improvement that might otherwise be missed by a human. Now, let's examine the output of our AI, the Docker file.recommended. This file is the heart of the optimization. It's not just a basic Docker file, it incorporates several key strategies. First, a multi-stage build. This is crucial for Java applications. We use a JDK image for the build stage to compile our code, and then a much lighter JRE image for the final runtime stage. This ensures our production image only contains what's absolutely necessary, dramatically reducing its size. Second, layer caching optimization. Notice how the pom.xml is copied and dependencies are downloaded before the source code. This means if only the source code changes, Maven dependencies aren't re-downloaded, speeding up subsequent builds. Third, security. The Docker file sets up and runs the application as a non-root user, significantly mitigating potential security risks. Finally, it includes JVM tuning parameters, Java_OPTS, specifically tailored for container environments, ensuring the Java application performs optimally within Docker's resource constraints. These are the kinds of expert-level optimizations that an AI can consistently apply. To demonstrate this in action, our project includes a build.sh script that orchestrates the local execution flow. First, it triggers mvn clean package to compile our Java microservice into a fat.jar, the deployable artifact. Next, it calls python3 recommend_dockerfile.py, simulating the AI's analysis and generation of the optimized Docker file. This is the pivotal moment where the AI's recommendations become tangible. Finally, Docker build f_dockerfile.recommended uses this AI-generated Docker file to construct our Docker image, followed by Docker run to launch the container. A quick curl http://localhost 8080/API/hello confirms that our AI-optimized Java microservice is up and running. This streamlined process clearly shows how an AI can inject optimization directly into your local development workflow, making it effortless to generate robust and efficient container images from the start. The real power of AI-driven Dockerization truly shines when integrated into a CI/CD pipeline. Our GitLab ci.yml file provides a practical example of how this can be achieved. The pipeline is structured into several distinct stages: build Java, AI recommend Docker file, and Docker build push. The build Java stage, as its name suggests, compiles the Spring Boot application. Critically, the AI recommend Docker file stage then executes our python3 recommend_dockerfile.py script. This means the AI generates the optimized Docker file as part of the automated pipeline execution. The resulting Docker file.recommended artifact is then passed to the Docker build push stage, which uses it to build and push the final, optimized Docker image to a container registry. This ensures that every single build is automatically optimized, eliminating manual intervention and guaranteeing consistency across all deployments. The benefits of adopting AI-driven Dockerization are profound and far-reaching. Firstly, optimization. Images become significantly smaller, reducing storage costs and accelerating deployments. Build times are slashed due to intelligent layer caching. Secondly, consistency. Best practices for Docker files are uniformly applied across all your microservices, regardless of the developer. Thirdly, speed. The manual effort of crafting and refining Docker files is eliminated, allowing developers to focus on core business logic. Fourthly, adaptability. as Docker best practices